Hello everyone, in the fourth part of our experiments, we are going to try and verify Ohm's law. In order to do that, we are going to construct a basic circuit that consists of a resistor and a power supply. The current is flowing to this direction, the resistance is R, the power supply has potential V. Now in his experiments, Ohm realized that when he increased the potential that the power supply produces, the current that's generated is increased proportionally, meaning the current is equal to a constant times the potential. Now, this constant is called the conductance, or in other words, 1 over R. This R is defined as the resistance. Putting it back into the equation, we have V equals I times R, which is the Ohm's law. Usually, writing this equation as I equals V over R, we can immediately see that the current is directly proportional to the potential, and it is inversely proportional to the resistance in the circuit. Now in the experiment, in order to verify the Ohm's law, we are going to increase the potential and measure the current for each potential value. If our resistance is ohmic, we are going to find out that the curve is going to be linear, and the slope is going to give us 1 over R, the resistance in the circuit. In the next part of the experiment, we are going to try and analyze Kirchhoff's laws. Now, for some circuits that are complicated, we cannot find the equivalent resistance in the circuit easily. Therefore, in order to analyze the circuit, we have to apply Kirchhoff's law. There are two laws. The first one is called the voltage law. It states that the potential drops across a closed loop is equal to 0. Now, in order to see this more clearly, we can reconstruct our circuit that we used in the previous part with a voltage supply V and the resistor R. Then we are going to have to assign a current to the circuit. For this easy circuit, it is logical to assume that the current flows in clockwise direction. However, the choice of the direction of the current is arbitrary. If, after applying the voltage law and solving the equation that comes after, what we find is the current value is bigger than 0, then our initial assumption is correct. If we find that the current is smaller than 0, or a negative value, it means that the current is flowing in the opposite direction. Now let's apply the Kirchhoff's first law to this circuit. I'm going to start from this point and then move clockwise and then come back to this point. Now, if I start from here, now I come to this resistance. Now I am moving in the direction of the current, which means that I am going to have a potential drop, meaning I am going to have I times R with a minus sign. Then after leaving this resistor, I am going to come to my power supply. I am going to enter from the negative sign and exit from the positive sign, which means I am moving from a lower potential to a higher potential, which is going to increase the potential. So I'm going to have plus V equals 0. Reconfiguring this, I'm going to have V equals I times R, which is Ohm's law. Kirchhoff's second law is called the junction rule. It is sometimes also stated as the current law, which says that the amount of current that enters a junction is equal to the amount of current that leaves the junction. In order to see this more clearly, let's have a junction here. And I have two currents, I1 and I2, entering the junction, and three currents, I3, I4, and I5, leaving the junction. So according to the junction rule, I'm going to have I1 plus I2 equal to I3 plus I4 plus I5. Now, in order to analyze Kirchhoff's law, we are going to work on a circuit that has a specific name, which is Wheatstone bridge. A Wheatstone bridge is a circuit that is constructed like this. I have R1, R2, R3, R4, and R5 with a potential V. Now what I need to do is assign a current to each branch. Here I assign I1 to the branch with the resistor R1. Here are I3, here I2, here I4, and here I5. In this current diagram, I have 5 currents that are unknown. I1, I2, I3, I4, and I5. Now, as an example, I am going to write one of the equations that we can use to solve for these current values by using Kirchhoff's law. I am going to name these branches first. Here's A, B, C, D, E, and F. Now, in order to give you a good example, I am going to choose A, and then C, and then B, and then D, E, F, A loop. What I'm going to do is, I'm going to start from here, this point, and then move along this branch, follow this route, then go back to where I started. As I move along this path, I have a current which is in the same direction with my loop, so I'm going to have a potential drop I3 times R3. When I come to C, I'm moving upwards, but the current is moving downwards, so I'm going to have an increase in potential. Therefore, this plus I5 times R5. Now I'm moving from B to D. I'm moving in the same direction with the current, so I'm going to have a drop in potential, I2 times R2. And then from D to A, E, from E to F, I have an increase in potential, an amount of V. And then I'm back at where I started. Therefore, the sum of these potential drops must be 0. Now your task is to construct 4 more equations like this and then solve for it. Now let's try and see what makes this Whetstone bridge special. Let's just assume, for the sake of convenience then, I5 is equal to 0. So at junction B, from the junction rule, I have I1 coming in and I5 and I2 coming out. So I need to have I1 equal to I2 plus I5. Since I assume that I5 is equal to 0, therefore I can write I1 equals I2. And at junction C, I have I3 and I5 coming in, I4 leaving, therefore I3 plus I5 is equal to I4. Since this is 0, I'm going to have I3 plus I4. Now I'm going to construct two loops. One is this loop, which is called ABCA. Now let's use Kirchhoff's law on this loop. From A, I'm going with the direction of the current, so I'm going to have a drop in potential, which is minus I1 times R1. Now at this point, I assume that I5 is equal to 0, therefore there is no change in potential here. So I come to C, and from C to A, I'm moving in opposite direction of the current, therefore I'm going to have an increase in potential, which is going to be I3 times R3 equal to 0. From here, I can write I1 times R1 is equal to I3 times R3. Now another loop is going to be this one, which is from B to D to C and then back to B. B, D, C, B. Now as you remember from here, I2 was equal to I1 and I4 was equal to I3. So here I'm going to have a drop in potential because I'm moving in the same direction as the current. So minus I1 times R2, and here I'm moving in the opposite direction as the current, so I'm going to have an increase in potential, which is I3 times R4, which is equal to 0. Therefore, I'm going to have I1 times R2 equal to I3 times R4. Now I can divide these two equations side by side to get, let's write it here, I1 times R1 over I1 times R2 equal to R3 times R3, I3 times R4. I1s cancel out, I3s cancel out, I have R1 over R2, which is equal to R3 over R4. Or I can write this like this, R1 times R4 is equal to R2 times R3. Which means that if in a Whetstone bridge, if I have the currents that are across from each other, if their multiplication is equal to each other, then I'm going to have no current passing through this branch, or in other words, I'm going to have no potential difference between point B and point C. Now, how can I use this? Usually, the way I use this is like this. I have R1 and R2. These two are variable resistors, and this R3 here is fixed. And then I have a resistor here for which the resistance value is unknown, which is called Rx. And I'm going to put a voltmeter here and connect this to a power supply. So what happens is, by adjusting the values of R1 and R2, my aim is to get a reading of 0 from here. If I do that, then I can write R1 times Rx is equal to R3 times R2. So the value of the unknown resistor is Rx R3 times R2 over R1. So a whetstone bridge can help me find the value of an unknown resistor.
Okay, in this experiment we are going to talk about firstly Ohm's law, and then we are going to continue with Kirchhoff's two rules. In order to analyze the Ohm's law, we are going to use the simple setup which is given in figure 14.19 in the lab manual. This circuit consists of three elements, one of which is the DC power supply, and then comes the digital ampere meter, and finally the ohmic resistor, whose resistance we don't know yet. And the aim of the experiment is to analyze the current through this resistor and the voltage across these resistors terminals. And if we plot current versus voltage, the slope of the graph is going to give us the resistance value. So the setup is like this. This is the leads of the power supply, which is a DC power supply. We are going to apply different values of voltages, DC voltages, across the terminals of this ohmic resistor, and we are going to measure the resulting current through this circuit element. In order to measure the current, we are going to use this digital multimeter, ampere meters mode, and then we apply a 2 volts voltage across this circuit element, which is the resistor, and the resulting current is 5.75 milliamps for 2 volts. And then we increase the current step by step. The next voltage value is 4 volts. For ohmic resistors, we expect to see that the current through the resistor increases linearly with the applied voltage. As you can see, if we double the voltage, we see nearly double the current. So it is 11.57 milliamps for 4 volts. Again, we increase the voltage to 6 volts. And we see that the current increases to 17.27 milliamps. Next, we increase the voltage to 8 volts. So you see that we are above the 20 milliamps range. So we increase the range to 200 milliamps. And we see that for 8 volts, 24.1 milliamps is the resulting current that's flowing through this resistor. For 10 volts, we will see that the current increases to 30.3 milliamps. And finally, for 12 volts, the resulting current value is 36.4 milliamps. So this is the data taking part. Next, we will analyze this data and we will find the resistance value of this resistor by plotting the resulting current versus applied voltage, and the slope of this graph is going to give us the inverse resistance value. We ideally use ohmic resistors. For ohmic resistors, we expect to see a linear relationship between the current and voltage. Okay, in this part of the experiment, we are going to investigate Kirchhoff's two rules. These two rules are Kirchhoff's voltage rule and Kirchhoff's current rule. Kirchhoff's voltage rule states that the sum total of all voltage drops around a closed loop should be equal to 0. And Kirchhoff's current rule or junction rule states that the total current that's going into a junction should be equal to the total current that's coming out that same junction. In order to analyze Kirchhoff's these two rules, we are going to use a simple bridge circuit, which is given in the 14.20 of lab manual. This bridge circuit is a basic setup which has been used to measure the unknown resistances in the 1840s or 1860s. A different version of this, not exactly the same one, but very similar one. In this setup, we are going to designate our resistors in the table 14.11. The R1 resistor is this one, which is 100 ohms. The R2 resistor is this one, which is equal to 330 ohms. The R3 resistor is again 100 ohms. The R4 is 330 ohms, and R5 is the bridge resistor, which is 560 ohms. First of all, we are going to measure the total resistance of this bridge circuit. In order to do that, we use the multimeter in the resistance mode. As you can see, the total resistance value is 0.218 kilo ohms, which is equal to 218 ohms. And next, we are going to apply some voltage across these two terminals, and we are going to measure the resulting voltages across each of these resistors so that we can later on analyze the circuit in terms of Kirchhoff's voltage rule. So we set our DC power supply to 4 volts DC and apply our voltage across these two terminals. In order to measure the voltages, we use the DC voltage mode of our multimeter. So this is our positive lead and this is our negative lead of multimeter. So multimeters are whose voltage we are going to measure. So I hope you can see. So the voltage across R1, which we denote as V1, is 0.93 volts. Okay. So V2 is 3.06 volts, and V3 again 0.92 ohms across R4, which is V4 is equal to 2.92 ohms. The voltage across R5 is 0 volts, and the voltage across the whole circuit is 3.95 volts, which is not exactly 4 volts as we should see. That means that there's a calibration difference between our DC power supply voltmeter and our digital multimeter. So you may ask why the voltage across this bridge resistor is 0 volts. That's a special setup. That's why the voltage across this bridge resistor is 0. This special setup is called the Wheatstone bridge setup. When the ratio of this resistor to this resistor and the ratio of this resistance to this resistance equals to each other, we see zero current or zero voltage drop across this bridge resistor. And finally, we are going to measure the currents through these resistors. In order to do that, we are going to change the lead arrangement of our multimeter, and we are going to set it to ampere meters mode. So first of all, let us measure the total current running through this circuit. Remember that ampere meters are connected in series with the circuit element that we are going to measure the current through. So we break the circuit and we reconnect the circuit with our ampere meter. So the total current through this circuit is 18.6 milliamps. And so next, let us measure the current through this resistor. In order to do that, we again break the circuit and then reconnect it using the multimeter. So the current through R3, or we may call it I3, is equal to 9.3 milliamps. Okay, let's measure the current through R4. Again, we break the circuit and reconnect it using the multimeter. We see that the current through R4, which is I4, is equal to 9 milliamps. And then let's continue with I1. Let's break the circuit like so and reconnect it using the multimeter. We see that the current through R1 is 9.3 milliamps. And the current through R2 is going to be 9.3 milliamps. And finally, the current through the bridge resistor is going to be 0. Why is that so? As we have seen in the previous measurement of voltages, we measured the voltage drop across this bridge resistor to be 0. So if you have 0 voltage drop across a circuit element, you expect that current through that same circuit element should be 0. In this part of the video, we are going to analyze the data we have taken. We will begin with Ohm's law. During the experiment, we have applied different values of voltages across a resistor and we measured the resulting currents. When we plot the current versus voltage graph, we see that we get a linear relationship between them. The slope of this line gives us the value of 1 over R as 2.9873 milliohms. And from there we get the resistance value as 334.75 ohms. We have used a 330 ohms resistor in the experiment, so we see that our measurements are pretty accurate. And let's continue with the Kirchhoff rules experiment. We have used this circuit in the experiment. Our resistors were 100 ohms, 330 ohms as R2. As R3 we were using 100 ohms and R4 was 330 ohms. Again, R5 was 560 ohms. We measured the resulting currents I1, I2, I3, I4 and I5. When we apply Kirchhoff's current rule at the node A, we should have the total current, which is IT, entering in the junction A should be equal to the sum of I1 and I3 that's going out that junction. And when we replace the data we have taken during the experiment, we see that 18.6 milliamps was total current flowing in the circuit. I1 was measured to be 9.3 milliamps and I3 was measured to be 9.3 milliamps again. And we see that their sum equals total current IT. At node C, we should have I1 equal to the sum of I2 plus I5. So when we replace the values, 9.3 milliamps is equal to I2 was 9.3 milliamps again, and we measured that the current flowing through the resistor R5 was 0 milliamps. So we see that the Kirchhoff's current rule at the node C is satisfied again. At node D, again, the current that's going into the junction D should be equal to the current that's going out. The incoming currents are I3 and I5, and I4 is the current that's going out. So when we replace the values again, 9.3 plus 0 is equal to 9 milliamps. At node B, again, the incoming currents are I2 and I4, and the current that's going out is the total current IT. When we sum the I2 and I4, we see that that's nearly equal to 18.6 milliamps. When we apply the Kirchhoff's voltage rule, we should sum the voltage drops around a loop, closed loop. When we consider the loop A, C, D, A, we see that the voltage drop from A to C is V1, and the voltage drop from C to D is V5, and from D to A we see a voltage rise, which is V3. We should sum them up, and we see that their total should be equal to 0, and the voltage drop V1 was 0.93 volts. Since there is no current in the resistor R5, the voltage drop should be 0, and the voltage rise from D to A is 0.87 volts. So when we sum them up, we should get nearly 0 volts. So we see that Kirchhoff's voltage rule is again satisfied for loop ACD. For loop CBD, the voltage drop from C to B is V2. From B to D, we see a voltage rise, V4. From D to C, we again should see a voltage rise, but since there is no current in R5, V5 is 0 again. So V2 should be equal to V4. And we see that nearly Kirchhoff's voltage rule is again satisfied for loop CBD. For loop ACBD, from A to C, we see a voltage drop, V1. From C to B, we see again a voltage drop, V2. From B to D, we have a voltage rise, V4. From D to A, we again have a voltage rise, V3. When we sum them up, we should get 0. And again, as we see, we nearly get a 0 value. And we can conclude that Kirchhoff's voltage rule is again satisfied for this loop.